Good day. Now we will be answering problems from chapter 21, electric charge and electric field. We will answer problem numbers 21.61, 21.65, and 21.75. So for the first problem 21.61, a charge Q1 with a charge of positive 5 nanocoulomb is placed at the origin of an XY coordinate system. So this is Q1. And the charge Q2, negative 2 nanocoulomb, is placed on the positive x-axis at x is equal to 4 centimeters. If a third charge Q3, positive 6 nanocoulomb, is now placed at the point x is equal to 4 centimeters and y is equal to 3 centimeters, find the x and y components of the total force exerted on this charge by the other two. Part B, find the magnitude and direction of this force. So to answer that, let's have the force diagram. So Q1 is positive and Q3 is positive. So they will repel, and the force exerted by Q1 to Q3 is this F1. F1 has two components, F1y and F1x. Then Q2 is negative and Q3 is positive. Therefore, they will attract. Then the force is F2 towards Q2. To answer this, we will use the Coulomb's law with this Coulomb's constant. Solving for F1, we have F1 is equal to the Coulomb's constant. Then we will multiply it by the two charges, Q1 and Q3, and divide it by the square of the distance between the two charges. The distance between the two charges, Q1 and Q3, is 0.05 meters. Inputting the values, we have the Coulomb's constant here, Q1 and Q3, and the distance. Calculating it, we will get 1.079 times 10 to the negative 4 Newton. So that is the value of this force, F1. Solving for the angle, this angle and this angle are equal. Since we had a right triangle, we can apply trigonometric function. We will choose sine and we will use the opposite side and the hypotenuse. To get the angle, we have arc sine opposite divided by hypotenuse. Inputting the values of the opposite, 0.03 meters divided by the hypotenuse, 0.05 meters, we will get 36.9 degrees. Now, solving for the components of F1, this F1, we will get this F1y and F1x. For F1x, this is positive because it is to the right. We will use the cosine function, cosine theta, because it is adjacent, and we will get 8.63 times 10 to the negative 5 Newton. Now, for the F1y, the y component is upward, therefore positive. We will use sine because it is opposite of the angle. And we will get 6.48 times 10 to the negative 5 Newton. Solving for F2, this F2. We have F2, Coulomb's constant, Q2, Q3 all over R sub 2 squared. So the distance between the two charges is 0.03 meters. Inputting the values, we will get 1.20 times 10 to the negative 4 Newton. The components of F2, obviously, it has no x component. Therefore, F2's x is 0. And then F2y is negative because it is downward. We have negative 1.20 times 10 to the negative 4 newtons. Solving for the x and y components of the total force exerted on Q3 by Q1 and Q2. So we will solve these components, the total force. So we have F sub x equal to F1x plus F2x. So we will just add the components along the x-axis, and we have 8.63 times 10 to the negative 5 newtons. For the y components of the force, we have F1y plus F2y, and adding them, we will have negative 5.52 times 10 to the negative 5 newtons. Then find the magnitude and direction of the total force. Finding the magnitude, we have this formula. F is equal to square root of the sum of the two components, and it is squared, and we will get 1.02 times 10 to the negative 4 newton. And for the angle, we have this tangent phi fy all over fx, and we will get phi, or the angle of the force, or the total force, is 32.6 degrees, and that is below the positive x axis. Okay, next problem, problem 21.65. We have a small 12.3 gram plastic ball is tied to a very light 28.6 centimeter string. So this is the plastic ball with a mass of 12.3 grams, and the string is 28.6 centimeters that is attached to a vertical wall of a room. A uniform horizontal electric field exists in this room. When the ball has been given an excess charge of negative 1.11 microcoulomb, you observe it remains suspended, with the string making an angle of 17.4 degrees with the wall. Find the magnitude and direction of the electric field in the room. To answer this, let's have first the force diagram. The ball experiences tension from the string, and it has two components, Ty and Tx. There is also an electric field, and this is the electric force due to the field, and the ball has weight. The electric field exerts a horizontal force away from the wall on the ball. The forces on the ball, which are gravity, tension, and electric force due to the field, add to 0 since the ball remains suspended. Since the ball is in equilibrium, or at rest, then the summation of forces along x is 0 as well with the summation of forces along y. Now let us solve for the x component. So as you can see in this diagram, we have the electric force and the tension along x. So since the electric force is to the right, it is positive here, and since the tension along x is to the left, it is negative here. So we have the electric force minus t sine theta is equal to 0. Substituted the value of t sub x here. And rearranging this equation, we have the electric force is equal to the tension sine theta. Now for the y component, we have these forces, the tension along y, and the weight. Adding the two, we have t sub y minus mg. Ty is positive because it is upward, and since the weight is negative, we have negative mg here. Substituting the value of Ty, we have t cos theta minus mg is equal to 0. Rearranging this equation, we have tension is equal to the weight divided by cosine theta. Now combining these two equations, we will have the electric force is equal to the quantity weight divided by cosine theta multiplied by sine theta. We just substituted the value of t to this t. We have this sine theta divided by cosine theta, and we know that it is equal to tangent theta. Therefore, we have electric force equal to the weight multiplied by tangent theta. And substituting the values, we have the mass of the ball, we have the acceleration due to gravity, and then the value of the angle is 17.4. So tan 17.4 degrees. Solving this, we have 3.78 times 10 to the negative 2 newtons. Now, since the electric force is equal to the absolute value of the charge times the electric field, we can rearrange this to get the electric field value. So, substituting the values, we have this electric force divided by the absolute value of the charge. Computing this, we have 3.41 times 10 to the 4 Newton per Coulomb. Since the RQ is negative and the electric force is to the right here, our electric field is to the left of the figure. Problem 21.75. Consider a model of a hydrogen atom in which an electron is in a circular orbit of a radius r, 5.29 times 10 to the negative 11 meter, around a stationary proton. What is the speed of the electron in its orbit? So to solve this, we will use these constants, the Coulomb's constant, the magnitude of the electron's charge, and the mass of the electron. The charge of the proton is the same with the charge of the electron. They only differ with the sign. Proton is positive, while electron is negative. We will use Coulomb's law, and since the electron is orbiting the proton, we will use the centripetal force and radial acceleration, or the centripetal acceleration. Now, substituting the radial acceleration with this, we will get centripetal force is equal to mass times velocity squared over r. Since the centripetal force is due to the attraction of the positive charge and the negative charge, it is also equal with the electric force. So, K E squared, this is E squared because, as we said before, the magnitude of the charge of the proton and electron are the same. So we have Ke squared over r squared is equal to mv squared over r. Rearranging this to get the velocity of the electron, we have v is equal to square root of Ke squared over mr. Substituting the values, we have the Coulomb's constant here, the electron's charge, or the magnitude of the electron's charge, the mass of the electron, and the distance between the two. Solving this, we will get 2.19 times 10 to the 6 meter per second. So this is the velocity of our electron.